Welcome back to another lesson in MCV4U. Today we'll be looking at our third lesson of optimization, which looks at time, distance, and speed. So in this first example, we see that Anna's house is 9 kilometers west of Bob's. At 8 a.m., Anna starts jogging south at 8 kilometers per hour. At 8:30 a.m., starts jogging west at 10 kilometers per hour. At what time it's the distance between Anna and Bob the smallest? After Bob has started jogging. Okay, so the first thing we'll do here was to draw our diagram. So here we know that Anna's house is 9 kilometers west of Bob's. Here we label A for Anna, and here we'll label B for Bob. And again, at 8 a.m., Anna just starts jogging south at 8 kilometers per hour. So here we'll write the speed is equal to 8 kilometers per hour. And that's, so again, Anna starts jogging at 8 a.m. And Bob at 8:30 a.m. starts jogging west at 10 kilometers per hour. So Bob's speed here is equal to 10 kilometers per hour. Here, again, at what time is the distance between Anna and Bob's the smallest after Bob has started jogging? So here, again, you see that Anna starts jogging south as well at 8 kilometers per hour. So we can draw the line down. Then Bob at 8:30 a.m. starts jogging west at 10 kilometers per hour. So Bob will start jogging west, and we'll indicate that with this red line. And here we're looking for the distance, again, where there's the shortest distance and at what time. Here we see that. Here we'll create a 90-degree angle triangle. And we'll label a couple of the sides. So we'll label this A, this is B, and here we know that the distance from Anna to Bob's house is 9 kilometers. So this entire thing is 9 kilometers. And so that means that this side would be 9 minus B. And then here we'll label the hypotenuse in this situation D as distance. And so here we're looking for, again, the minimum distance. And that's what we do. Let's let statements on a few things. So we'll let A represent distance and traveled. And this is in kilometers. We'll let B represent the distance Bob ran. In kilometers. And then we'll let D represent the distance between between them. So between Anna and Bob, again in kilometers. And here we'll let T, so this is different. So here we'll let T represent the time since 8 a.m. And this will be in hours. So here, using the Pythagorean theorem, we can write here again that d squared, so d squared is equal to a squared plus 9 minus b squared. Okay, and here we don't again have a direct relationship. So we don't have a direct relationship between A and B. And so here what we'll do is we'll relate both to time. Okay. And so here, if we recall the distance, speed, and time, remember we know that speed is equal to distance over time. We know that distance is equal to speed times time. And here, therefore, we know that in this situation, A is equal, so the distance is equal to the speed, which is 8 kilometers per hour times time. So we know that A is equal to 8t, and in terms of B, we know that B is equal to 10 times t minus 0.5 because Bob left a half hour later. Okay, so here we expand this, we know that B is equal to 10t minus 5. Okay, so now we're going to sub that back into our equation of d squared is equal to a squared plus 9 minus b squared. So here we sub those back in. Here we can write that as d squared is equal to a squared, so 8t squared plus 9 minus 10t minus 5 squared. So here, if we expand this, d squared is equal to 64t squared plus 14 minus 10t squared. Okay, so here we get d squared is equal to 164 t squared minus 280t plus 196. Okay, so here this is going to be a very messy derivative. So here, what we can see is that since d has to be greater than 0, So since d is greater than 0, we can optimize. We can optimize d squared. So here, and then we'll use implicit differentiation here, so we'll make it easier. Okay, so here we can do the derivative. So we'll do the derivative of, so d over dt, so the derivative of d squared with respect to time, we'll get 328 e minus 280. Okay, so here we'll get 328t minus 280. And so let's make that equal to, so we'll make that equal to 0. So we'll let d of d squared over dt equal to 0. So here 0 is equal to 328t minus 280. Move 280 to the other side. It's equal to 328t. In this situation, we see that t will be equal to 0.8537, and that will be in hours. So here, what we want to do is we're going to multiply this by 60 to get it into minutes. And so here we get a value of 51.22 minutes. Here, what we can do is then we can see that if Bob runs the full amount, so if Bob runs the full amount, so that's again if b is equal to 9, we see here that b is equal to 10t minus 5. And so sub in 9 for b. 9 is equal to 10t minus 5, and t is equal to 1.4. So here, if we sub that back into our equation, so d squared is equal to 164 times 1.4 times 1.4 squared minus 280 times 1.4 plus 196. We see that d is equal to 11.2 kilometers. So that's if Bob runs the full amount, that would be 11.2 kilometers. And so here, if we look at that, here we see that, again, this is Anna and Bob, and that's 9 kilometers apart from the houses. If he runs the full amount, this would be 11.2. In this case, we see that we got the time is equal to 0.8537 hours. So let's find that particular distance, which would be the minimum distance. So here, that distance, so if we do d squared is equal to 164 times 0.8537 squared minus 280 times 0.8537 plus 196. We'll see here that the distance will be 8.7 kilometers. So here we can see again that if we add the 51.22 minutes to the 8 a.m., we'll see here that approximately they are closest together at 8:51 a.m. 8.7 kilometers apart. And here, if we wanted to check that, again with our second derivative test here, just to double check. So second derivative test, we see here that the second derivative is equal to 328, again, which is greater than 0. And so here, that means it's positive, and therefore it is concave up, and therefore it provides us with the minimum value, which is what we were looking for here. So now let's take a look at this second question. So it says you are a competitor and survivor. Your challenge this week is to beat the other team in a rowing/running race. Your boat is located at the furthest end of one of the river banks. Furthest end of one of the river banks. From there, you must row across the 200-meter wide river, a 200-meter wide river, and then run to the finish line located at the end of the opposite shore. The shore is 500 meters in length. You know that you can row 1 meter per second, and you can run at 2 meters per second. You may choose to row across the river at whatever angle you would prefer. What is the minimum time that would take you to reach the finish line? Okay, so here, if we draw our diagram again, so here, let's draw our riverbank. Okay, so here, we say this, we can get this as the start point. So for start point, again, we know that we're going to row 200 from meter wide river. So here, if we row 200-meter wide river, and then here we know that from there it's 500 meters in length to the opposite shore. So the endpoint, that's 500 meters here. Okay, and here we have again, our, and here we will represent x, and that's the amount of time that you're not running. So here, this point, or the green line, will be 500 minus x. Okay, so let's do a couple of let statements. So first thing, we'll let t be the total amount, time in seconds. We'll let r be the distance rowed in meters. And we'll let x be the distance not run in meters. Okay, and here again, we're trying to find the minimum time. So here, again, we're looking at total time, and the total time is equal to the time that was rode plus the time that was run. If we're looking at this R value here, to start, again, we can use Pythagorean theorem. And so here we see that we have 200 squared plus x squared is equal to R squared. And so here, R is equal to 4,000, so sorry, is equal to 40,000 plus x squared to the power of 1/2. Okay, so here we see that the time total is equal to, in the time that was rode. Again, remember time is equal. So here, okay, time is equal to distance over speed. And so the time that was rode, again, we can write as R over 1. We know that, again, here it's 1 meter per second. And the time that was run, again, will be 500 minus x over 2. Okay, so here, so take a look at this. You can sub the value back in. So here R is 40,000 plus x squared to the power of 1 over 2 plus 500 minus x over 2. So here we're going to rewrite this as 40,000 plus x squared to the power of 1 over 2 plus 500 over 2, which is 250 minus 1 over 2 x. Okay, so now we're going to find the derivative. And here we'll use implicit differentiation again. So dt over dx is equal, so the outside, so 1/2, 40,000 plus x squared to the power of negative 1/2, and then derive the inside, which will be 2x. And then the derivative of 250 is just 0, and then derivative of negative 1 over 2x would be just 1 over 2. Here, the 2x, we can simplify the 2 and the 1/2. So here we can rewrite it as x over square root x over square root 40,000 plus x squared minus 1 over 2. And here, in this situation, we'll make dt over dx equal to 0. And so 0 is equal to x over square root 40,000 plus x squared minus 1 over 2. And so just a note here, again, that dt over dx is never undefined. Okay, so let's isolate here. So here we get 1 over 2 is equal to x over square root 40,000 plus x squared. Here we'll cross multiply. So we'll get square root 40,000 plus x squared is equal to 2x. Now we'll square both sides. Well, here we'll get x squared plus 40,000 is equal to 4x squared. Move the x squared to the other side. We'll get 40,000 is equal to 3x squared. Divide both sides by 3. We'll get x squared is equal to 40,000 over 3. And we'll square root both sides now. And here, again, we're only looking for the positive value. Here, we're only looking for the positive value. So here we get x is equal to positive square root 40,000 over 3. Okay, and that'll give us here x is approximately equal to 115.5. So now what we're going to do in this situation, again, so if we look at the second derivative, it's going to be quite complicated. So again, since second derivative is complicated, here we'll use the endpoint test instead. Okay, so again, the extremes again would be 0 and 500 are the endpoints in this situation. So that'd be x is equal to 0 and x is equal to 500. So here, if we sub in x is equal to 0, then we'll get here is equal to square root x squared, which is 0 squared, plus 40,000 plus 250 minus 1 half x, which is 0. So here we get t is equal to 200 plus 250. And so t will be equal to 450 seconds. We'll look at if x is equal to 500, so sub that back in as well. T is equal to square root 500 squared plus 40,000 plus 250 minus 1 half times 500. I receive the 250 and the negative 250 will cancel out. So here we'll have square root 500 squared plus 40,000. And so t will be here approximately equal to 538.5 seconds. And so here now we'll sub in our value of 115.5 seconds into our equation. So let's do that here. So here we'll get t is equal to square root 115.5 squared plus 40,000 plus 250 minus 1 half 115.5. And here we get t is equal to approximately 423.2 seconds. And so here we see that even with the extremes, again, this value of 423.2 seconds is going to be our minimum. And so therefore, the minimum time to complete the race is 423.2 seconds. Then we can convert that to minutes and seconds. Again, if we take 423, divide that by 60, that will be equal to 7.05. And so here, that represents 7 minutes, and then the 0.05, multiply that by 60, which will give us 3 seconds. And so here, that would be 7 minutes and 3.2 seconds.